If we put a satellite into an orbit such that it's got a time period of 24 hours, sometimes they call that geosynchronous. It's matching the rotation of Earth. So if we do it right, a satellite with the same time period as Earth's rotation, it wouldn't have any relative motion compared to Earth. So this is like your Bell satellite or your ExpressView satellite dishes, the ones that we use for telecommunications. We can just point the dish, stick it to the side of your house, point it at a satellite, and since that satellite has the same time period of Earth, the dish will always remain pointed at the satellite. If the satellite, like a GPS satellite, had a quicker time period, then you would see that satellite sort of drift by over a night sky. If you're trying to track it, your satellite dish would have to move to keep that satellite in view. As opposed to geosynchronous, it's always going to appear in the same position in the night sky. You could point a satellite at it, a satellite dish at it, and you would always sort of get reception from it. The physics of it is similar to what, well, the same as what we saw for the GPS question. I'm going to restart it all though. Little things like the R goes from the center of M to the center of M. It's moving in a circle at some speed V. It's driven by gravity, but it's going in a circle, so it turns into a centripetal thing. Gravity is the only force, so gmm over r squared is equal to mv squared over r. The little m cancels, doesn't matter how heavy your satellite is, one of the r's cancels. So we get this school equation that v squared is gm over r. That's a function that connects our velocity to the overall height or the radius of the satellite. What's interesting about that is it's an inverse relationship. If a satellite is farther from Earth, its speed must be smaller. It's not linearly inverted, but as r changes, velocity changes in the opposite direction. This particular question, the way it's asked, I don't care about the speed. I'm asked about the height given a particular time period. So I need to go a little bit farther. We know when something's going in orbit, it's going at a constant speed, just in a circular path. So speed is the same as 2 pi r over time period. So we can say 2 pi r over time period. If we square that, that's equal to gm over r. When we clean that up, we get a 4 pi squared. We get an r squared over t squared. And then our gm over r. Cleaning that one up, we get the gmt squared equation. I'm not big on memory work, but I've had students in the past just memorize that one. And when a satellite question comes up, they know they can use the gmt squared, 4 pi squared r cubed. These days, I don't think you got to memorize anything. You should be able to rederive it, but if you can't, just use your resources and re-find the equation you need. We're given the time period, we're going to solve for the r, then use the r to find the height. One little thing was the time period was given in 24 hours. We need to convert that to seconds. There are 86,400 seconds in a day. We're going to solve for r, and then I'll deal with the height. R cubed is going to be the g multiplied by the mass of Earth multiplied by that time period in seconds, and then divide all that by 4 pi squared. I just jumped to the final answer, so watch your order of operations. Oops, somewhere in here there's a square. The time squared. You got to do a cubed root at the end. But at the end of all this, I got a number of 42.23 times 10 to the 6. I'm writing it a little bit funny. My calculator said 4.223 times 10 to the 7, but just to help my brain see it, I'm going to put it as 10 to the 6. The reason is to get the height above the Earth, I'm going to take that number, 4223 times 10 to the 6, and subtract the radius of the Earth, 6.37 times 10 to the 6. By writing it that way, I can kind of see it a little bit better. The 6 lines up with the 2, so it's 42 and change. Take away 6 and change. I get 35.9 times 10 to the 6 meters. Or we could say 3.59 times 10 to the 7 meters. Or probably a better way to say it is if we put it in kilometers, it's 35,900 kilometers. That's the satellite question. Start with gravity equal to mv squared over r, and then sub in as you need to go.